so we are now done with volumetric analysis. Right, so under your learning objective, if you know how to apply stoichiometry for volumetric analysis, you put a tick. Okay, so actually it's the same thing. The idea of chemical calculation is always to use mole ratio from balance equation. Okay, then you use the 3 equation, which is the molar mass. Okay, the one that you use molar mass to calculate the number of moles, or you use molar volume for gases. And then for aqueous state, you use concentration to calculate the number of moles. Okay, so you are using these 3 equations interchangeably to find out what is the unknown. Unknown mass, unknown volume, unknown concentration. Okay, so moving on to the next part, we'll take a look at limiting reagents. Okay, so for this lesson, we will focus on limiting reagents. Alright, so recap, stoichiometry is to determine the quantitative relationship. Okay, in other words, it's just mole ratio. Okay, so let's take a look. Back to this example, 2 cracker squares, 1 marshmallow, 3 chocolate squares. I can make 1 s'more. Now, okay, I'm asked to make 3 s'mores. Okay, so I'll need 9 chocolate squares, 3 marshmallows. So how many cracker squares do I need? Okay, so this is the same example. I'll need 6 cracker squares. Okay, of course, all multiplied by 3, according to the mole ratio. Now, what if I'm given this? Okay, so likewise, working the other way. Okay, so just now was from small back to cracker squares. Now I'm given this amount. Find out the number of s'mores I can make. Okay, so if you compare the mole ratio, the number of s'mores that I can make is 3. Alright, so what if I give you this? Okay, you are given 8 cracker squares, 4 marshmallows, and 9 chocolate squares. How many s'mores can you make? So you take a look. This is multiplied by 3. This is multiplied by 4. And this is multiplied by 4. Okay, so how many s'mores can you make? So is your answer 4 or 3? Which one? So I only have 9 chocolate squares. The maximum that I can make, the maximum number of s'mores I can make will be 3. Okay, so this means that, okay, this is the one that is affecting my product, my final yield. Okay, so why only 3 s'mores? Because this is my limiting reagent. Whereas for my cracker squares and marshmallow, okay, I only need 3, I only need 6, which means I have 2 excess cracker squares and I have 1 excess marshmallows. Okay, so in this scenario, we don't just have exact. In fact, we have 2 of them with excess amount. Okay, and the amount of s'mores that I can make is dependent on my limiting reagents. Okay, so from here, I can identify the limiting reagent is my chocolate squares, and then the excess will be cracker squares and marshmallows. Alright, so let's try again. If I have this number of cracker squares, this number of marshmallows, and this number of chocolate squares, how many s'mores can I make? This is times 4, this is times 3, this is times 4. So how many? Is your answer 3? If it's 3, good job to you. You are able to identify how much based on this mole ratio, and you are able to identify which one is the limiting reagent. So which one? Okay, so my marshmallow is the limiting reagent. Okay, and then my excess will be my chocolate squares and my cracker squares. So my final product, the final amount, is always dependent on the limiting reagent. Okay, so here we are looking at calculation. Okay, and we are looking at limiting reagents, because not all reactions they react exactly, and not all the time we use exact amount. So usually when we want to carry out some reactions, one of them will be in excess. So why is that so? Why do we want to ensure one is in excess? Okay, to fill in your blank, page 12. Okay, this is to ensure that the chemical reaction is complete. Okay, we want to ensure that we use excess to make sure that it's complete. So there is one reaction that you have learned, okay, where one of them is in excess. Can you all recall? Pause the video and recall. Okay, and that will be your salt preparation. And the method is your ABCM. Acid reacting with insoluble base, carbonate, and metal. Okay, so if you recall, for example, I want to make copper 2 sulfate salt. Okay, I use H2SO4 acid. I use copper 2 oxide. Alright, so I have my beaker of copper 2 oxide. Okay, and I add my H2SO4. My copper 2 oxide is in excess. So this is my limiting. So I want you all to really recall salt preparation. Why is this in excess? What do I want to achieve? Okay, I want to use up all my acid and then I filter out the excess. Okay, I want to remove all my acid to react them completely. Okay, so that the salt, which is copper 2 sulfate form, will not be contaminated. Unreacted acid. Okay, so that's why I add my copper 2 oxide in excess. Okay, so this is one of the reasons why we add something in excess and the other one limiting. Okay, so limiting reagent is the one that is completely used up. Okay, it determines the amount of product formed in the reaction. Okay, so the final amount is dependent on the limiting reagent. Okay, the one in excess means they are not used up. So let's take a look at this reaction. Okay, I have magnesium reacting with sulfuric acid. So I form my salt and I form my hydrogen. So from mole ratio, I know that this is 1:1. 1 mole of magnesium will react with 1 mole of acid. However, if I want to react 1 mole of magnesium and I give 2 moles of sulfuric acid, so this is in excess. Okay, and I know from the mole ratio it's definitely 1:1. Okay, so even if I provided it with 2 moles, there will be 1 mole there is excess that was left behind. So from here, can you identify which one is the limiting, which one is the excess? The limiting reagent will be your magnesium. And the one in excess, because it's left behind, is your sulfuric acid. This is the same as the small example. So just now we make cracker squares, chocolates, marshmallow, all these are the same. Same concept. Okay, so 1 mole of magnesium react with 1 mole of acid, you will form 1 mole of salt. So this amount of salt is dependent on the limiting reagent, which is my magnesium. Okay, so I need to calculate limiting reagent. I will always refer back to my mole ratio. Okay, always refer back to the mole ratio. So concept is always the same, which is using mole ratio stoichiometry. Okay, so question is, how do we know which one is the limiting reagent? We need to calculate. Okay, so if I go back to the previous slide, okay, it is very clear cut that my sulfuric acid is excess. Okay, it is very clear cut that my sulfuric acid is in excess because 1 mole is 1 mole and then I given 2 moles. So we are always comparing moles. I repeat, we are always comparing mole using mole ratio. Okay, so let's take a look. Okay, now from here, okay, I know that only 3 smalls can be formed because I identified my limiting reagent to be my, which one is the limiting reagent? To be my chocolate squares. Okay, I have my mole ratio here, I compare. So I always compare the number of units, number of moles, and then this is times 3, the rest is times 4, which means this times 3 is the one that's limiting. Okay, so if I were to do it in a chemistry question, okay, how should we do it? So in chemistry, you are given in mass, you are given in volume. You must always convert it to number of moles. Okay, you're always supposed to convert it to number of moles because you're using mole ratio. Okay, so this is inside your notes. First of all, always write down the balance equation. They tell you that magnesium is combusted. Combusted means you react with oxygen and you form magnesium oxide. So this is the balance equation. With all the reactants and products balanced properly, you can get the mole ratio. Okay, so this is your balance equation. Then you're given magnesium, you're given oxygen. So now, take note, you're given two values, You're given two values. So you need to calculate the number of moles for both of them. You need to calculate the number of moles for both of them. Okay, because you don't know which one is the limiting. Because you're given both values. Previous example, if you look back, you're only given one value. Okay, so first of all, you need to calculate. So since both values are given, you don't know which one is in excess, which one is limiting, so you need to calculate. Then you can compare mole ratio. Okay, so number of moles of magnesium, mass over molar mass, 6.25 moles. Number of moles of oxygen, volume over molar volume. Okay, molar volume, because it's a gas, it's 2.08. Okay, so now you need to compare the mole ratio. 2 moles of magnesium react with 1 mole of oxygen. 2 moles of magnesium react with 1 mole of oxygen. So from here, from this value, it's not very easy to see. Because just now, previous example, you can see exact values. But in this case, the values are not exact. So it's a bit hard to calculate. So what I do is, I will determine the mole ratio. Okay, first of all, 2:1:2. Okay, I don't know which one is the limiting reagent. I just choose one. I just assume. Okay, I'm going to use magnesium first. Okay, look here carefully. Magnesium to oxygen is 2:1. If I have 6.25 mole, because I'm given this amount. This amount means 6.25 moles of magnesium. So 6.25 moles of magnesium will require 3.125. Okay, 6.25 moles of magnesium will require 3.125. Okay, but how much are you given? How much of oxygen are you given? You need 3.125 to react with this amount of oxygen. Okay, you need 3.125 oxygen to react with this. But you are only given 2.08. I repeat, you are only given 2.08. Is it enough? It's not enough, right? So at this point, you should roughly see already, it's not enough. To react completely with 6.25 moles of magnesium, you need 3.125 of oxygen. But you are only given 2.08. So, at this point, you should see that oxygen is the limiting reagent. Okay, so I'm just assuming I'm using magnesium.
Okay, if I don't want to use magnesium, I can also use oxygen.
Okay, so if I use oxygen, 2 moles is to 1 mole. For every 2.08 mole of oxygen, I will need 4.16 moles of magnesium. I will need 4.16 mole of magnesium. And you compare, you see now. I need 4.16, but you are given 6.25. So this means that it is more than enough. Do you see that? This means that it's more than enough. Okay? So more than enough means that magnesium is your excess reagent. Okay? So at this point, I need to write this statement. Oxygen is the limiting reagent. Oxygen is the limiting reagent. Okay? So, I identify the limiting reagent. I need to calculate the amount of product, the mass of product formed. So I have two values. I have either magnesium or oxygen. So which one do I use? Do I use the one in excess to determine the amount of product? Or do I use the one that's limiting to determine the amount of product? So you recall just now, we talked about the biscuit, the s'mores. The final product, the amount of product is always dependent on the limiting reagent. Okay? So, have you heard of this quote? You're only as fast as your slowest team member. So, sports people usually in the relay, you will be able to identify this, or you will be able to relate to this. Okay, in the relay, of course, the slowest person is the one that determines how fast the team is. Then in chemistry, Miss Bay say one. Okay, Miss Bay say the yield of the product is only as much as the limiting reagent. Okay, so the yield of the product is only as much as the number of moles of limiting reagent. So it's always dependent on the limiting reagent. Okay, so since oxygen is the limiting, we use the number of moles for oxygen. So we compare using oxygen to this. magnesium oxide. So the number of moles is 1:2. Okay, so if the number of moles of oxygen is 2.0881, magnesium oxide times 2 will be 4.16. Okay, so I need to find the mass. So I multiply mole times molar mass, I get the mass, 23SF. So this is how I calculate. Okay, so I repeat, for limiting reagent, we need to identify the limiting reagent first. Okay, so when you're given two values, you need to identify the limiting reagent first. Then you can calculate. Students tend to forget this step. Students tend to forget that they need to find out what is the limiting. They just calculate straight away using either one, which is not correct. Okay, so please take note. Once you're given two values, you need to calculate the limiting reagent. Okay, so when do we need to determine? Because the question will not tell you. The question will not tell you, oh, this is the limiting, this is the excess, because you are required to compare and identify. So previously, look at your notes previously. Okay, previously you are only given one value. Okay, previously you are only given one value. So there's no way. There's no way you can identify limiting reagent because you're only given one value. So limiting question, okay, limiting reagent questions, they will give you two values. Okay, that you need to identify. Okay? Okay, I would like you all to try out limiting reagent question. Can you turn to your notes, page 14, question 1. So likewise, using the guide in your notes, complete this question by yourself. 4 to 5 minutes. Okay, by yourself. Okay, so once you are done, you check your answers. Okay, so first of all, you are given this. Okay, you are given the equation. Alright, so you want to find the maximum mass of calcium carbide that can be formed. So can you see that you're given two values, 160 grams of calcium oxide, 180 grams of coke. Okay, so since you're given two values, it means that one of them is in excess. So you calculate. Calcium oxide, mass over molar mass. Okay, this is 40 plus 16. You get 2.857 moles. Number of moles of coke, 180 divided by 12, which is your carbon, you get 15 moles. Okay, so from here, I compare these two first. I need to identify which one is the limiting reagent. So mole ratio will be 1:3. So from here, I don't know which one is the limiting, which one is the excess. So I just use, for example, calcium oxide first. So every 1 mole of calcium oxide, I will need 3 moles of carbon. I will need 3 moles of carbon. So if I have 2.857 moles of calcium oxide, multiply by 3, I will need 8.571 moles of carbon. I will need 8.571 moles of carbon. Okay, and how much are you given? You are given 15 moles of carbon. You're given 15 moles of carbon. But you only require 8.57. So at this stage, are you able to identify which one is the limiting, which one is the excess? Yes, right? Okay, you given 15 moles, but you only need this. Okay, so carbon is in excess. So I try again using carbon. So if I have 15 moles here, for every 3 moles of carbon, I only need 1 mole. So for 15 moles of carbon, I will need 5 moles of calcium oxide. I will need 5 moles of calcium oxide. And you are only given 2.857. So at this point, are you able to identify which one is the limiting, which one is the excess? Okay, so I can identify that the limiting reagent is calcium oxide. Okay, because here, if I use carbon, 15 moles, I only need 5 moles of calcium oxide, but I'm only given 2.8. So it's not enough. So the one that's not enough is the limiting reagent. Okay, so this is how you present your answer. Okay, you can either write this statement using calcium oxide or you can use this statement. Either one statements will do. Then you can identify the limiting reagent. So from here, I know that calcium oxide is the limiting. I will use calcium oxide to compare. I'll use calcium oxide to compare. So calcium oxide versus calcium carbide, mole ratio is 1:1. So for every 2.857 moles of calcium oxide, 2.857 moles of calcium carbide will be formed. So I don't stop here, I need to calculate the mass. So actually it's the same thing. Okay, to calculate the mass, I'll need molar mass first. So 40 plus 2 times 12, get 64 gram per mole. 64 gram per mole. So I have 2.857 mole. I have 2.857 mole. So I multiply them together, and my 3SF is 182 grams. So the maximum mass of calcium carbide is 182. Okay, so this is for question 1, page 14. Okay, so remember, the amount of product formed is always dependent on the limiting reagent. Okay, now page 13, let's look at gases. Now for gases, it's more straightforward. Okay, remember when it's gas, we only just use volume ratio. Okay, because they're all gaseous state, we can use volume ratio. Okay, so we just use volume ratio to calculate. So first of all, you are given this equation. Okay, you are given two values. Okay, notice you are given two values. Alright, I don't know which one is in excess. Okay, so for every mole of propane, I will need 5 moles of oxygen. So 1:5. Okay, so I don't know which one, I will just use either one. So if I use propane, so for every 10 cm cube of propane, I will need 50 cm cube of oxygen. I will need 50 cm cube of oxygen. But how much are you given? You are given 70. So this means that it's more than enough. More than enough. You only need 50 to react with 10 cm cube. And then you are given 70. So at this point, you can identify that my oxygen is in excess. And then if you don't believe yourself, you try using oxygen. Okay? If I use oxygen, 70 cm cube of my oxygen, I divide by 5. Okay, I will need 14 cm cube of my propane. And then you are only given 10. You are only given 10. Okay, which means that it's not enough. So at this point, limiting reagent is my propane. Limiting reagent is my propane. So if I want to calculate the volume of carbon dioxide formed, I must use the limiting reagent. Okay, so I must use the volume of my limiting reagent. I compare propane and carbon dioxide directly. So mole ratio is 1:3. So if my propane is 10 cm cube, okay, I use volume ratio because they are all gases. They are all gases. I'm not looking at my water. I don't care. Okay, so I'm looking at my gases. 1 mole is to 3. 10 cm cube times 3 will be 30 cm cube. So volume of carbon dioxide is 30 cm cube. Okay, so try the next question. Question 2, page 14. Likewise, don't look at the answer first. Try it yourself first. Okay, so first of all, let's try. Okay, balance equation will be hydrogen plus oxygen. And then you form water, which is H2O. Okay, so to balance this equation, I will need 2 hydrogen. And then I form my water, which is liquid state. My oxygen is gas, hydrogen is gas. Okay, alright, so mole ratio, this is to 1. Okay, now I'm given two values, 125, 50 of hydrogen. So I don't know which one, I will just choose one to compare. Okay, I can use volume ratio because they are all gases. So this is my mole ratio. I can also use volume ratio. Okay, so using hydrogen, okay, if this is 50 cm cube, I will need 25 cm cube of oxygen. Okay, using hydrogen, if this is 50 cm cube, I will need 25 cm cube of oxygen. And how much am I given? I'm given this. So it's more than enough. So at this point, I can identify that oxygen is in excess. So if I don't want to use hydrogen, I use oxygen. So I write down here using oxygen. If I have 125 cm cube here, I will need 250 cm cube of my hydrogen. I will need this. Okay, but how much am I given? I'm only given 50. So at this point, I can tell that hydrogen is the limiting reagent. Okay, so I will need to write this down. Okay, so the question is asking, what is the gas that we made? What is the gas that we made? Okay, so I know that oxygen is in excess. Okay, so oxygen is the gas that we made. So the gas remaining is oxygen. Okay, so hydrogen is the limiting reagent. So if I have 50 cm cube, if I have 50 cm cube of hydrogen, 25 cm cube of oxygen will react. 25 cm cube of oxygen will react. Okay, so the question is asking, what is the volume of the gas that we made? What's the volume of the gas that we made? Okay, so if you look here, you are given this, you're given 125 cm cube. And you only used up 25 cm cube. Okay, so volume of oxygen remain. Okay, you are given 125 cm cube. You use up 25 cm cube to react with the hydrogen. You are left with 100 cm cube of oxygen. So to SF. Okay, so this is how you calculate excess and limiting reagent. Okay, alright, so we are done with limiting reagent. Okay, so from here, okay, we actually use stoichiometry to calculate. And this time round, we bring in the idea of limiting reagents. That means one can be in excess and then the other one will be limiting. Okay, reason why we use in excess is to ensure that the reaction is complete, to ensure that one of them is completely used up. Okay, so we are done with limiting reactants. Okay, we are moving on to the last part, percentage U and percentage purity. Okay, so calculate percentage U and percentage purity. Percentage U is to find out whether this reaction is it feasible, is it economical, because we are always trying to aim for higher percentage U. Okay, we don't want to have a reaction that maybe only produce 1% U. That's not feasible. Okay, there's a lot of wastage. Then when we produce something, we aim for 100% purity. Okay, so why is it important? Of course, money. Okay, we want to react. Companies, they want to produce something, they expect high percentage U. Otherwise, there will be a lot of manpower wastage, a lot of chemicals wastage. Okay, so let's take a look. Now, percentage U, we try to aim 100%, but of course, in reality, it's very hard. Okay, so in this reaction, magnesium reacts with oxygen to form magnesium oxide. So theoretically means on paper, by right. Okay, when I react with 2 moles of magnesium, excess oxygen, so mole ratio will be 2:2. Okay, so theoretically, I should get 2 moles of magnesium oxide. But in actual fact, I'll get less than that. Okay, there can be many different reasons. Incomplete reaction, impure reactants, okay, loss of product during the reaction when I transfer from one apparatus to another, maybe you spill something. Okay, all these are probable reasons why we don't get 100% U. Okay, so in chemical reactions, we try to reduce all this. We try to aim for higher percentage U. Okay, so it's important that when we do something, we calculate, see whether is method A better or method B better. Okay, maybe both methods can produce this. Okay, we want to see whether method A has a higher percentage U or method B will have a higher percentage U. Okay, so theoretical U is the calculated amount of product formed. Okay, that means it's on paper. By right, when we calculate, it should be like that. Okay, actual U is the amount that is actually produced in a reaction. Okay, so percentage U will connect these two together. Okay, so actual U will always be less than theoretical U. It can never be greater. Okay, so on paper, if I get 100%, actual U cannot be more than 100%. It doesn't make sense. Okay, that means it's calculation error already. Alright, so how to connect them together? Percentage U means the amount that I actually produce over the theoretical amount times 100%. Okay, if theoretically I'm supposed to get 1 kg of product and in actual reaction I have 1 kg of product formed as well, which means this reaction 100% U. 100% U. Okay? Or instead of the mass, I can also look at the number of moles. Theoretically, I should get 10 moles. Actual reaction, I also get 10 moles. This means that my percentage U is 100%. Okay, so I can either use actual mass or I can use number of moles. Okay, they are both referring to quantities. So you want to use mass or number of moles, they are both the same. Okay, either one is correct. Alright, so let's take a look. So in this question, you are supposed to get 60 grams of crystals. Supposed to get, huh? So this 60 gram will be your theoretical U. And then actual U, you only get 45 gram. So percentage U will be 45 divided by 60. Okay, easy. So this is how you calculate. Alright, so let's try one question. Okay, so let's take a look at this example here on page 15. Okay, you are given 13.1 gram of calcium oxide that's produced. Okay, so 13.1 gram of this is produced when you heat 25 gram of calcium carbonate. Okay, so first of all, you want to find percentage U, right? This is the actual produced, actual amount. You need to have the theoretical amount to calculate the percentage. Okay, so I use either this or this, either one, recall. Okay, so moving on. This is my actual U, fill in the blanks. I want to determine the theoretical U. Okay, so how to calculate? Actually, it's the same thing. It's the same as what you have learned previously. So I have 25 gram. I use 25 gram. So I use 25 gram. I want to find the number of moles. Okay, 1 mole of this will produce 1 mole of this. So I need to find the number of moles of this first. So I started off with 25 gram. 25 gram divided by the MR, molar mass, is 0.25. Okay, so mole ratio is 1:1. So if it's 1:1, 0.25 mole of this will mean 0.25 moles of my calcium oxide. Okay, so theoretically, I should have this number of moles produced. Okay, so what is the theoretical mass? Okay, so since 0.250 moles of calcium oxide is formed, okay, you need to find the theoretical mass. Okay, so I find the theoretical mass. So from 0.250 moles, theoretically, I should get 14 gram. Okay, so this is my molar mass. So theoretically, I should get 14 gram. But in actual fact, only 13.1 is produced. Only 13.1 is produced. So I need to calculate what is the percentage U. Okay, so actual U is 13.1. Theoretical is 14. So 13.1 divided by 14. Okay, so 13.1 divided by 14 times 100%. Okay, the percentage U is 93.6 to 3SF. Okay, so this is how I do it. Or I can change this number of moles. I can change this to number of moles, and then I use this one is my theoretical number of moles. And then this is my actual number of moles. So I can use the other equation to calculate. So both are fine. Okay, so try question 1 on page 16. Likewise, pause your video. Okay, give yourself 5 minutes to complete. 4 to 5 minutes. Okay, so in this case, you are given sulfur dioxide and it reacts with oxygen. So this is the balance equation. So they tell you 140 gram is produced. So this is the actual U. Okay, so you are supposed to calculate what is the theoretical U. Alright, and then this is the mass given to you. So what you need to do is, of course, you need to calculate the number of moles. So 128 gram of SO2, okay, mass over molar mass, 128 gram divided by your molar mass, which is this, okay, and you will get 2 moles. Okay, so SO2 versus SO3, mole ratio is 2:2. Okay, so if you have 2 moles of SO2, you'll produce 2 moles of SO3. Okay, so number of moles of SO3 is 2. So this is the theoretical number of moles. Okay. So what is the theoretical mass? What is the theoretical mass of SO3? Okay, so you calculate number of moles, multiply by molar mass, okay, which is 32 plus 3 times 16 gram per mole, and you will get 160 gram. So this is your theoretical mass. But actual mass is this. Okay, so what is the percentage yield? So percentage yield will be actual mass is 140 gram. Theoretically, you produce 160. By right, you should. But you only produce 140. So what is the percentage yield? Okay, so the percentage yield is 87.5% to 3SF. Please remember your unit. Okay, so same thing. Can you pause video? Give yourself 5 minutes to complete the next question. This one, okay? Complete the next question. Pause the video first. Don't look at the answer, okay? So you are given 6.5 gram of zinc to make zinc sulfide. And 9 gram of zinc sulfide is obtained. So same thing. Calculate the number of moles of zinc first to find out by right how much you should make. So 6.5 gram divided by 65 gram per mole, you'll get 0.100 mole. So zinc, to make zinc sulfide, is 1:1. 1 mole is to 1 mole. So if you are only given 0.100 mole, you will produce 0.100 mole of zinc sulfide. Okay? So number of moles of zinc sulfide is 0.100 mole. What is the mass of zinc sulfide? Okay, so number of moles multiplied by the molar mass, which is 65 plus 32 gram per mole, equals to 9.7 gram. So this is your theoretical mass. But how much are you only produce? Actual yield is only 9. So percentage yield, so actual is only 9 gram. By right, you should have 9.7 gram. So you multiply by 100%. Okay, your percentage is 92.8% to 3SF. Okay, so this is how you calculate. Alright, okay, so this is what we call percentage yield. Okay, next, page 17, last part already, percentage purity. So why is percentage purity important? Okay, let's take a look at this. Okay, you have gold. So I don't know whether you are aware that there's such thing called 999K gold or 91.2K gold. Okay, so you have 9 karat gold, 10 karat gold, and 24K gold is the finest. Okay, it means 100%. Okay, which is quite soft. Okay, but jewelry, they don't really use 100%. The more expensive one will be 999. Okay, then the lower the percentage, the cheaper it is. Alright, so not just for gold. Now, percentage purity is also important, especially in terms of medicine. Okay, you don't want to produce a medicine that's not pure. Okay, otherwise it will impose health problems for those consumers. Okay, so let's take a look. Now I have this reaction. Okay, I have 1 gram of pure calcium carbonate. Experiment 2. I have 1 gram, same mass of impure. So my question to you is, which experiment will produce a lesser amount of carbon dioxide gas? What will your answer be? Both have the same mass, but one is pure, one is impure. Okay, experiment 2. Okay, because it is contaminated with impurities, and this means that in actual fact there is lesser amount of calcium carbonate present. So lesser amount of carbon dioxide will be produced. Okay, so purity of a substance affect the yield of the products. So if I use really pure substances, okay, then I will have more of my calcium carbonate, then I will produce more of my carbon dioxide. Okay, so the more impure the reactants, the lower the actual yield. Alright, so the percentage purity will be We want to see how pure the substance is. So it will be mass of the pure sample versus mass of sample. For example, if I have 10 gram of sample, and out of this 10 gram, the whole 10 gram is pure. So the percentage purity will be 100%. Okay, if my sample is 10 gram, and out of this 10 gram, only 9 gram is the one that I want. The remaining 1 gram is impurity. So which means the percentage purity is 90%. Okay? So, how do we work in chemical reactions? So here they say 100 grams of calcium carbonate was reacted with excess, okay, sulfuric acid. So in this case, this is my limiting. Okay, the question say percentage purity. Once the question asks percentage purity, it means that this sample is impure. I repeat, once the question asks you to calculate percentage purity, you need to assume that they are impure. Which also means this 100 gram contains impurities. Okay, so let's take a look. Likewise, the steps are always the same. We always calculate by using the balance equation first. Okay, so we get the balance equation, okay, to calculate the mole ratio. So they tell you 20 grams of carbon dioxide is formed. 20 grams is formed. Okay, so we need to work backwards. Because this is impure. This 100 gram is impure. That means it contains something else. So we cannot find the number of moles directly. Because it's impure. Okay, I repeat, because it's impure, this 100 gram contains impurities. So it is an accurate value already. So what we do is we use the amount of product form. Because if you look back, the yield of the product is dependent on the pure substance. It's dependent on the pure sample. Okay, so we cannot use 100 gram. Okay, what we do is we have to use carbon dioxide. Okay, so the product is formed from calcium carbonate. So we work backwards now. Okay, so we work from the product to find out. Okay, so 20 grams of carbon dioxide, I use mole ratio. I need to calculate the number of moles. Mass over molar mass, which is 44 here, 44 gram per mole, calculated to be 0.455 moles. I use mole ratio. Okay, so this is 1:1. So for 0.455 moles of carbon dioxide produced means that 0.455 moles of calcium carbonate is used. Okay, I repeat. For every mole of carbon dioxide formed, 1 mole of calcium carbonate is decomposed, is reacted. Okay, 1 mole of calcium carbonate is reacted. So if my mole of carbon dioxide is 0.455, for my calcium carbonate will also be 0.455. Okay, so 0.455 moles reacted. What is the mass? Okay, so I multiply by the molar mass. Okay, the mass of my calcium carbonate is 45.5. So this is 100. Okay, so what does this mean? So out of 100 gram, 45.5 gram is pure calcium carbonate. Okay, I repeat. This is impure, contains impurities, but we don't know what is the percentage. So I have to work backwards. I know that 20 gram of carbon dioxide is formed. I calculate the number of moles first. Okay, and then I use my mole ratio to find out the number of moles of calcium carbonate. From there, I can calculate the mass, the pure amount of calcium carbonate. Okay, so out of 100 gram, 45.5 gram is calcium carbonate, which also means only 45.5% purity. Okay, so using this as a guide, okay, let's try the first question in page 18. Okay, we can try this together first. Okay, let's try question 2 first. Okay, let's try question 2 first. So you are given 20 gram of zinc sulfide. Okay, 12.96 gram of zinc oxide is produced. Calculate percentage purity. So once you see this word, it means that my zinc sulfide is impure already. Straight away is impure. Okay, so I calculate. First of all, I can't use this value anymore because it's impure. And I don't know what is the percentage because it's contaminated by something else. Right, so I calculate from zinc oxide directly. Okay, so I have mass over molar mass. Okay, so my mass is 12.96 gram. Molar mass will be 64 plus 16 gram per mole. Okay, so the number of moles is 0.162 moles. Okay, so this is my number of moles of zinc oxide. So I do my mole ratio, zinc oxide versus zinc sulfide. So zinc sulfide is to zinc oxide. Okay, from the equation is 2:2. I simplify will be 1:1. So if I have 0.162 moles of my zinc oxide, this is produced by reacting 0.162 moles of zinc sulfide. Okay, so this amount is reacted. So from here, what is the mass of zinc sulfide? So I use the number of moles multiplied by the molar mass, which is 65 plus 32 gram per mole. Okay, so the mass will be 15.714 gram. Okay, I leave it to about 5 SF so that my answers are accurate. So from here, to produce this, to produce this mass of zinc oxide, I will need 0.0162 of zinc sulfide. And this 0.162 of zinc sulfide, the mass is 15.714. 15.714. Okay, so out of 20 grams, okay, so out of 20 gram, 15.714 is the zinc sulfide. So if I calculate the percentage purity, okay, to find out what is the percentage purity, the percentage is 78.6% to 3SF. Okay, so this is how I calculate. Alright, okay, now pause your video, give yourself 5 minutes. Okay, give yourself 5 minutes to try question 1. Okay, try question 1. Pause the video and try out yourself. Okay, so in this case, they are saying that you have impure. So actually straight away they tell you it's impure already. Now this question is slightly different. They gave you the percentage purity. Okay, so they tell you that it's impure. So copper react with air. So this air refers to oxygen. Okay, so copper reacts with oxygen. You form copper 2 oxide. Okay, now even if you don't know what this air means, okay, even if you don't know what this air, you don't know that this air is referring to oxygen, you ask yourself, copper to form copper 2 oxide. Copper to form copper 2 oxide, you are adding oxygen. So it means that it's reacting with oxygen. Okay, so you are given 4.8 grams of copper, of impure copper. So 95% purity. Okay, so you are going to find out of this 4.8 gram, okay, out of this 4.8 gram, actually you only have 4.56 gram of pure copper. So it's a little bit different for this question, but the idea is the same. You are still using percentage purity. So I have 4.56 of pure. Now I can calculate. Now I can calculate the number of moles of my copper. So how to calculate the number of moles of my copper? Mass over molar mass. Okay, which is gram per mole. So 4.56 gram divide by molar mass, or my atomic mass, is 64 gram per mole. Okay, the number of moles will be 0.07125 moles. Okay, so I compare mole ratio because I want to find out the copper 2 oxide, how much is formed. So copper to copper 2 oxide is 2:2. I simplify it to 1:1. If I have 0.07125 moles of copper, I will have 0.07125 moles of copper 2 oxide. So the question is, what is the mass? So mass of copper 2 oxide will be 0.07125 moles multiplied by my molar mass, okay, which is 64 plus 16 gram per mole. I calculate. The mass will be 5.70 gram, 23SF. Okay, so if you compare question 1 and 2, they are both percentage purity, but I can phrase it in a different way. But actually, they are all using the same thing, which is percentage purity. Okay, which is percentage purity. Okay? Okay, so we have done percentage yield and percentage purity, and that marks the end of our chemical calculation. And good job for completing them. Okay, it's not easy. It takes a while, so practice makes progression. Alright, so complete all questions in the chemical calculation notes and also try out the questions in the worksheet.